to you and to Gnosis builders for the support of this ZK hackathon. And we're looking forward to seeing what you have to say about that.
Yeah,
so I'll let you.
Cheers. Thanks for having us. Yeah, so hey everyone, I'm Auryn. I work at Gnosis and Gnosis Guild. We build a whole bunch of different infrastructure for the Ethereum ecosystem, along with being the kind of custodians of Gnosis chain. Today, we're going to chat through mostly bridge-related topics and kind of introduce something called Hashi that we've been working on for the last few weeks. So it's kind of relatively new, very exciting. So yeah, we'll just dive right in. So Hashi is this system for additive security for cross-chain bridging. So what we'll do here is just go through a brief intro to Hashi, kind of talk briefly about why bridges get hacked, have a chat about the kind of Hashi design principles and goals, the architecture, and then talk through your challenge for the hackathon. Maybe in between there as well, we can actually just dive into the Hashi code a little bit and go through it, or we can wait till after and do it kind of with Q&A. I am totally cool with this talk getting derailed. If you have questions, don't feel like you have to wait till the end. You can throw them in the Q&A section, throw them in the chat. And yeah, feel free to derail me anywhere. We can go down rabbit holes, and I can always make my way back to the talk yeah, afterwards. So I guess with that, we'll dive right in. So introducing Hashi. Hashi is this protocol for cross-chain communication based on additive security. Essentially, it's aggregating multiple inputs, multiple oracles. At its core, Hashi has a typo in the presentation. Hashi is a oracle. It's a hash oracle aggregator. So it allows one to implement what, as of about 30 minutes ago, we're calling a RIHO, a redundant array of hash oracles. And so the goal here is to distribute trust for bridges on the mechanism level, to essentially not have to trust any one individual bridge mechanism, or allow end users to kind of set up this layer of redundancy on the bridge mechanisms that their systems depend on. So why Hashi? Why do bridges get hacked? So in 2022, there was roughly $2 billion worth of tokens lost in kind of bridge-related exploits. 4 of the top 5 exploits that are on the rec.news leaderboard are bridge-related exploits. What I think this should be a kind of really clear indicator of is that essentially no bridge implementation is 100% secure. And that we probably shouldn't be building security critical systems that depend solely on any of them. All bridge designs have some trade-offs in terms of cost and security and auditability and all these kind of things. And so, yeah, the kind of really important kind of take-home message here is that the systems built on top of bridges get hacked or get exploited because they put all of their trust into individual bridge mechanisms that ultimately get exploited. And that's not to say that every bridge mechanism will ultimately get exploited, but every bridge mechanism has an attack surface. None of them are 100% secure. And so for security critical applications, it really doesn't make sense to put all of your trust, essentially make your system entirely dependent on the security of one individual bridge mechanism. So the design principles for Hashi, essentially we want to standardize at the lowest level, the hash, and we can kind of dive into what we are talking about when we talk about hashes here a little bit later. We want it to be modular and agnostic to the underlying mechanisms. And we want to enable this thing, RIHO, a redundant array of independent hash oracles. So this is analogous to a RAID, redundant array of independent drives. If you've ever dealt with kind of setting up servers or anything like that, then you would have played around with this, where essentially if you have a critical piece of data, right? You have a system that has some data that is critical. You wouldn't just store that kind of on the solid state drive in your laptop or on a flash disk. You would want to kind of create backups of it, essentially. So you might store it on your laptop, you might store it on a flash drive as well, you might upload it to a cloud storage provider. You might store it on multiple of your own machines, or you might set up a RAID. So a RAID is this system where you have multiple disks running in parallel, storing all of the data so that if one of the disks breaks, the others still have the data. Depending on the configuration of the RAID, you can also get speed gains as well as redundancy gains out of it. But in either case, it kind of has this trade-off of kind of speed, cost, and redundancy, or I guess this trilemma kind of thing, where you can kind of get two of the three most of the time. And so, yeah, what we're trying to set up here is this kind of system, or what we're trying to enable, I should say, is the system that's analogous to RAIDs, but for bridge oracles, where you get this kind of choice now to kind of optimize for whichever two of those three things you want. In our case, we very much want to optimize for security over latency and cost, where a Raiho is going to kind of move only as fast as the slowest oracle in whatever the kind of threshold set is that you need to kind of agree on a hash. And because of that, because especially if you're using kind of a threshold of more than one, robustness and security are kind of going to be improved, but at the cost of increased resources. And so I guess stepping back a bit, I'll stick here for a second. So the design of Hashi is essentially, analogous to this RAID setup. Kind of multiple bridge oracles need to report the same hash, or I should say multiple hash oracles need to report the same hash in order for your system to consider that hash valid. What set of oracles need to report it is entirely kind of up to you as the person implementing a system built on top of that, built on top of this kind of Raiho setup. And yeah, we can dive more into that once we start poking through some code in a little bit. So the goals here, we want kind of diversification on the cross-chain protocol implementation. We want to have many different mechanisms that we're aggregating in order to come up with a valid hash for any given data that we want to validate across chains. And the idea here is that these mechanisms should be both independent and kind of diverse, so that it's the kind of more independent they are and the more diverse the implementations are, the more difficult it is for a would-be exploiter to coerce those mechanisms into reporting something false at the same time. If the mechanisms are, if it's duplicate implementations of the same system, then kind of breaking both at the same time is kind of much more likely. So we want kind of a good mix of things like committee-based oracles, ZK oracles, optimistic oracles, so that it becomes really difficult to exploit all of them simultaneously in the same way, have them all report the same false information. We want to see integrations, I guess, yeah, so with that in mind, we want to see integrations with kind of multiple head oracles, telepathy, zkBridge, et cetera, integrations with multiple message passing mechanisms, AMB, wormhole, et cetera. And we want to allow kind of users the choice in which combinations of mechanisms to trust to secure their systems. So quick kind of overview of the architecture. This looks really messy, and it kind of is, and this is to a certain extent the price you pay for additional security, but we can kind of walk through it. I'm not sure if you guys can see my mouse cursor or not. I'll assume that you can. But on the left-hand side, starting with a kind of canonical example, the token bridge. So we have some token bridge contract that wants to ultimately mint tokens on a kind of destination chain, right? So on the source chain, it's going to send a message or put a message into storage, and that message is then going to be reported over a variety of different mechanisms to the destination chain. On that destination chain, each of these mechanisms is going to essentially validate the message independently, validate a hash of the message independently, and then that will be aggregated by Hashi, and the token bridge contract will ultimately request from Hashi a validation of, request from Hashi the hash that is associated with a given kind of message ID or block ID, and if they all agree on it, then allow tokens to be minted. I am being a little bit, I don't know, obtuse in how I'm talking about this, because it's not just for this use case. We started building this thinking about how do we aggregate block headers? How do we aggregate the hash that is attached to every block, so that on a destination chain we can validate, or on one chain we can kind of validate the state of another chain using kind of light clients or kind of other mechanisms that will report the block header. But in setting it up, we realized that it's kind of more general purpose than this, in that it can really just be used to aggregate any hashes that kind of conform to this mapping of bytes 32 for domain, uint 256 for ID, and then bytes 32 for the data. So if you have some data that you want to aggregate that can kind of map well to that structure, then yeah, you can build aggregators, or you can build Oracle adapters for it, and kind of use this architecture to build kind of redundancy into systems that are wanting access to that kind of data. So the main components here, I mean, at least what we're thinking about here is applications like token bridges, governance bridges, NFT bridges. The underlying components to that are the hash oracles, essentially the things that plug into other systems. So if we're talking about block headers, this would be the Oracle adapters that then plug into something like Succinct Labs telepathy client, or plug into the arbitrary message bridge or the wormhole bridge to grab messages or block hashes. The core contracts for Hashi are the Hashi contract, which is this kind of stateless, very unopinionated way of just querying multiple oracles or Oracle adapters from kind of one place. And then this zkBridge is this kind of governable extension to Hashi that lets you kind of have an ownable contract that you can define explicitly what set of adapters must agree on a given hash for the system kind of connected to it to consider it valid. And so this is where you would get this kind of zkBridge contract is where you would set up something like a RIHO setup. You would define the set of adapters and the kind of threshold, the number of those adapters that need to agree on a hash to consider it valid. Outside of that, systems built on this will probably also want to leverage things like storage proofs, reporter contracts for broadcasting and then executing messages based on the hash, and then relayers for listening to events on an origin chain and reporting the hashes or triggering the transactions on the corresponding destination chains. So what can you build with Hashi? What we'd like to see people working on is adapters for other bridges, preferably ZK Lite client bridges, but also we'd love to see kind of optimistic bridges and committee-based bridges and any other mechanisms that you can come up with. Again, diversity is really valuable here. We'd love to see contracts that check Merkle proofs for some events or storage on an origin chain. And we'd love to see alternate implementations of giri-giri-bashi. So it's a relatively simple kind of aggregation rule right now, but we'd love to see kind of different governance rules, kind of pausing mechanisms, different aggregation rules. So yeah, kind of variations on that contract, I think would be really great to see. And then we'd love to see things built on top of Hashi. So token bridges, NFT bridges, governance bridges, and other novel things that that we're not thinking about. So yeah, just going through that again here, the challenge for you guys, you have these kind of two categories that I think are relevant. The category 5 is applications leveraging. I think in the hackathon description it said zkBridges, but changing it over here, we as much as we want to see ZK stuff, I think more so we want to see kind of diversity. So additional pieces that kind of allow for this Raiho setup, and then applications built on top of this kind of Raiho style setup. Yeah, I think from there we can move on. I guess, yeah, deliverables, so open source code, obviously, ideally well tested and documented. If it's something that's improving on Hashi, then PRs to the Hashi repo, so that's things like additional adapters and whatnot. And then, yeah, short presentation explaining the project. The prizes for each of the categories are published up on the Hackathon website, so I don't think we need to go over them now. There's a bunch of resources here in the presentation. I'll share the link to the presentation afterwards. There are deployed contracts here that we've listed. These are probably a little bit out of date now because we've been actively developing for the last few weeks, but they should work if you need them. I'd probably recommend just deploying your own rather than leveraging the ones that exist here. But if you don't want to deploy your own, then here they are. Yeah, that's the end of the talk. I'll jump over into the code. And again, if anyone has questions, then feel free to just kind of derail it. But we can jump in and just start kind of poking through what Hashi is, how it works kind of under the hood a little bit more, and kind of go from there. So Hashi is a really, really simple contract. Less than 100 lines of code, including a bunch of comments. The kind of primary function that you would interact with here is just get hash, where you're going to provide a domain. This is probably a chain ID, an ID here, which is probably the block number or kind of message ID, and then an array of adapters that you want to query to get the given hashes from. When you call get hash here, it's basically just going to iterate through the list of Oracle adapters and report back the hash if they all agree on it. If they don't agree, then the function is just going to throw an error that the oracles disagree. So super simple code, but yeah, this is kind of the base of what Hashi does. Giri-giri-bashi extends this a little bit, makes it ownable. Here we go, and gives you a little bit of storage to do things like define which set of adapters are valid for a given domain, and what the threshold of adapters is that's required for a given domain. And then it's basically going to expose the same endpoint, get hash. It will run a handful of its own checks to make sure that the threshold is high enough. There's no duplicate adapters. None of the adapters passed in are kind of invalid. Make sure that they all correspond to one of the adapters in the list for that given domain. And then it's going to call out to Hashi to make sure that the adapters that you've passed in actually agree on a given hash. So this is kind of the core pieces to Hashi that would exist on the origin chain, essentially the chain that wants to receive messages.
Auryn, we only see the thank you screen. Are you sharing some
Oh,
code? Yeah.
I am sharing some code. Good call out. Let me switch to a different screen. I've been just ranting on here. So I'm going to switch to here then. How's that like?
Yeah, now we see the code.
All right, perfect. So I'll jump back in here really quickly. This is our get hash function from our Hashi contract. Just to go over it again quickly, it's basically just going to take a domain, which is likely the identifier for the chain that you're wanting to query, so chain ID, and then ID here is probably the block number or message ID. Oracle adapters is the list of adapters that you want to query to get to aggregate a hash. And so when you call this function, it's going to iterate through this list of Oracle adapters and make sure that they all agree on the hash. And then Giri here is the ownable version of this that again lets you kind of set some internal state to define what set of adapters are valid for a given domain and what the threshold is that's required for a given domain to the threshold that's required for a given hash to be considered valid on a given domain. And again, it's going to expose the same function, get hash, perform a handful of checks before ultimately calling out to a Hashi contract to query each of the Oracle adapters. So these two contracts would be deployed on kind of each potential destination chain. And then on the origin chain, I guess, depending on whether if you're just querying for things like block headers, then nothing specific needs to be deployed on the origin chain. You just need on the chain that you're wanting to. I should clarify that. Depending on the mechanism, you probably don't need something deployed on the origin chain. For some mechanisms, like maybe a committee-based Oracle, you could have something deployed to kind of coerce message bridges into reporting block headers. I can show some code for that in a minute. But for kind of light client type setups, you wouldn't need anything specific deployed. For passing messages, on the other hand, you would have something like this contract here, Yahoo. This is our kind of message dispatcher. And what it's going to do is has a handful of functions here for dispatching messages, relaying already dispatched messages to adapters, and then kind of a convenience function for doing both in one call. But the idea here is that essentially when you dispatch a message, you're putting a hash of that message into storage and you're emitting the message dispatched event. And so depending on the Oracle mechanism, that should pretty universally allow just about any Oracle mechanism to have a route to validate that this message was actually passed from the origin chain. So some Oracle mechanisms may do things like storage proofs, in which case you've got this message in storage. Others may do things like event proofs. So you've had this event that's happened on the chain that you can now validate using event proofs, and then others might use want to kind of create a message from what's in storage and then pass it via some committee-based Oracle. So yeah, this Yahoo contract allows us to create a message that just about any Oracle mechanism should be able to validate through whatever its kind of local mechanism is. And then on the other side of this, if you're creating messages, then you probably are wanting to trigger some kind of execution from it. So this is our Yahoo contract is our message executor. And from this one, you can basically execute messages from Oracle. So if the Oracles report a a hash that corresponds to the messages that you input, then it will allow you to execute it. So essentially you put in an array of messages along with an array of message IDs, and this function here, execute messages from oracles, is going to iterate through your list of oracle adapters and query that the calculated hash from the messages that you inputted corresponds to the hash that's reported from each of the oracle adapters that's required, and if they do, then it will allow the message to be executed. And so from this, you would then, if you're building, say, a token bridge, it would plug into this. The token bridge on the origin chain would send a message through Yahoo to tell the token bridge on the destination chain to execute a message. The token bridge on the destination chain would receive a call from that was initiated by this execute messages from oracles, which is a permissionless function that anyone can call and will validate that the message passed in has not been executed yet and corresponds to the ID of the message that you pass in. Yeah, I guess that's a pretty good overview of the code and probably gives you a good starting point. The other place that we could take a quick look is at adapters here. So we have a handful of adapters that we've written already. A and B connects telepathy all pretty much ready. The wormhole one is not. We haven't written any tests for it yet. It's essentially just a sketch of what the code might look like. So if you're looking for some low-hanging fruit of somewhere that you might jump in and make some additions or improvements to this repo, fixing the wormhole adapter is probably a great place to start. But yeah, essentially adapters are going to inherit this Oracle adapter contract, and if they're a block header storage contract, then they'll also probably want to implement this or inherit this header storage contract. Sorry, no, they'll probably want to implement this block hash Oracle adapter contract that just allows for kind of historical provenance. But yeah, the idea here is that essentially each Oracle adapter should have a mechanism for storing the hash and then expose this function get hash from Oracle, which Hashi can ultimately call. Let's see. Oracle adapter.get hash from Oracle. So Hashi can ultimately call this when it is aggregating the reports from various different mechanisms. And so the route that it takes to do that for your Oracle adapter depends entirely on the mechanism that it's plugging into. The A and B adapter, for example, is basically just going to store hashes, but it's only going to allow the arbitrary message bridge contract to call that function and only allow it from a specific message sender on the origin chain. In that case, this is this A and B header reporter. So this is what I was talking about earlier, where we can kind of coerce message bridges into reporting headers if we want to kind of use them for that function. Yeah, I guess that's maybe a good stopping point or a good opportunity to jump into some of the chat questions. Yeah. And if we don't have any questions, then we can just wrap it up here. If you want to find out more about kind of Gnosis and Gnosis chain generally, then we've got a bunch of links here. there is a whole bunch of us available most of the time to answer any questions, and specifically for folks participating in the hackathon, we'll obviously be really responsive and yeah, do our best to help you find whatever information you need. All right, so we got a message here from Jin Park saying, can we explain how the coercing part works again? Absolutely. So I'll just go back to the code. All right, so when I say we're kind of coercing this this message passing mechanism to report block headers, essentially what we're doing here is we've got this contract AMB header reporter that we deploy on our origin chain, on the chain that we want to get block headers from, and it's got this function here, report headers. You're going to drop in the pass in the block numbers that you want to report headers on, and this contract is going to take take those inputs and essentially just call let's have a look here. Bear with me for a second. Okay, so our header storage contract here. So our AMB header reporter contract is importing header storage. So when we call report headers here, it is calling this store block headers function, which is going to call this global variable block hash, where we pass in the block number, and then it's going to put that hash into storage, and then allow us to kind of pass it over the message bridge. So this global function here, block hash, allows you to, at least in most EVM environments, allows you to query for the block hash of up to the last 256 blocks. So it has kind of a limited window of hashes that you're able to kind of have access to natively in this way. But it lets you, grab those block hashes and then put them into storage here. So kind of periodically calling this lets you have access to block headers then kind of indefinitely, because we're just dropping them into storage. Now, AMB header reporter is going to call store block hash or block header, sorry. And then once it's got the block headers for the block numbers that you've passed in, then it's going to create a message to send over the arbitrary message bridge store hashes call, and it'll pass it over the bridge with its required to pass message. And then on the other side of the bridge, where did we go? On the other side of the bridge here, our AMB adapter is going to, we're calling the store hashes function from the bridge, and again, it's only going to accept messages coming from the arbitrary message bridge that have the correct chain ID and the correct message sender on the origin chain. So yeah, I guess it's a long-winded way of explaining kind of how we coerce a message bridge into reporting block headers, or kind of one way that you can do this. It's a little inefficient because it requires you to kind of periodically poll the chain to kind of put the header into storage, but it works.
All right, well, I think that answered that question well. Does anyone else have any questions they want to drop in the Q&A? Doesn't look like it. But thank you, Auryn, for sharing all those resources as well. And please share those slides with us, and we'll be sure to get those to the students.
Yeah, great. I'll go ahead and just drop the slides in the chat here. Here's a link to those, and then yeah, make sure that it's available elsewhere as well.
Okay, great. Well, thank you very much for joining us this evening.
No worries. Thanks for having me, guys.
Yeah. All right.